this video, I'm going to show you how I built a simple but powerful calculator using the PIC 16F877A microcontroller. This project combines both hardware and software ideas that are very common in embedded systems, so it's a great learning example. The main components involved are the PIC 16F877A itself, a 16x2 LCD, and a 4x4 matrix keypad. The keypad is what we use to enter numbers and operations, and the LCD is where everything is displayed. Internally, the microcontroller scans the keypad, processes the arithmetic operation, and then sends the result to the LCD. Everything is written in microC, which is a very popular compiler for PIC microcontrollers. The nice thing about this setup is that it closely resembles how real embedded calculators and control panels actually work in practice. Now let me walk you through the code step by step and explain how it connects to the hardware. At the very top of the code, we define the LCD connections. The LCD is connected in 4-bit mode on port B. RB0 and RB1 are used for the RS and EN control pins, and RB2 to RB5 are used for the data lines D4 to D7. Right after that, we define the direction registers for those pins, telling the PIC that all these pins are outputs because the LCD only receives data from the microcontroller. Next, we move to the variables section. Here we define num1, num2, and result as unsigned long variables. These store the first number, the second number, and the result of the calculation. The variable called operation stores which arithmetic operation the user selected, like plus, minus, multiply, or divide. The variable key stores the value read from the keypad. The txt array is a buffer used to convert numbers into strings before displaying them on the LCD. There is also a bit variable called math error, which we use as a flag to detect cases like division by 0. Then we define len1 and len2, which store the number of digits in num1 and num2. These lengths are very important because they help us place the operator, the second number, and the equal sign at the correct LCD positions. Right after that, there is a small helper function called trim. This function removes leading spaces from strings produced by longtoostar. This is necessary because longtoostar pads numbers with spaces, and if we don't remove them, the text on the LCD shifts in strange ways. This function makes sure numbers always start exactly where we want them. Then we define the keypad layout. This is a 4x4 character array that represents what each key means. Physically, the keypad rows are connected to RD0 to RD3, and the columns are connected to RD4 to RD7. The characters in this array directly match what appears on the keypad, including numbers, operators, the clear key, and the equals key. After that comes the keypad scanning function, getKeypadKey. This function is one of the most important parts of the system. It works by driving one row low at a time while keeping the others high. Then it checks which column line goes low. If a column pin reads low, it means the button at the intersection of that row and column has been pressed. The function then waits until the key is released and returns the corresponding character from the keypad keys array. If no key is pressed, it returns 0. Now we move to the main function. First, ADCON1 is set so that all pins are digital. Then TRESB is set to 0, so port B works as output for the LCD. TRISD is set so that the lower 4 bits are outputs for the keypad rows, and the upper 4 bits are inputs for the keypad columns. The LCD is initialized, cleared, and a short welcome message is displayed. Inside the infinite loop, the program continuously checks for a key press. If no key is pressed, it simply continues looping. When a key is detected, the program decides what to do based on that key. If the key is C, everything is reset and the LCD is cleared. If the key is a number, the program either appends it to num1 or num2, depending on whether an operator has already been selected. The updated number is converted to a string, trimmed, and displayed at the correct LCD position. When an operator key is pressed, the operator is stored and displayed immediately after num1. For multiplication, the star symbol is converted to an X, so it looks nicer on the LCD. When the equals key is pressed, the program performs the calculation using a switch statement. If division by 0 is detected, the math error flag is set. Otherwise, the result is calculated normally. Finally, the equal sign is displayed at the correct position, and the result is shown on the second row of the LCD. If there is a math error message is displayed instead. After that, the calculator resets in a way that allows chain calculations, meaning the result can become the new first number. To demonstrate how the system works, I'll enter a few calculations on the keypad and show how the numbers, operator, and result appear cleanly on the LCD. You'll see that the layout behaves just like a real calculator. From here, there are many ways this project can be improved. We could add support for decimal numbers, include a backspace key, limit the number of digits to prevent overflow, or even store calculation history. In real life, this exact logic is used in devices like digital meters, vending machines, access control panels, and industrial control interfaces. So even though this looks like a simple calculator, the concepts behind it are extremely powerful and widely used in embedded systems. And that's the full breakdown of the PIC calculator project.